Hello. So if you can hear my voice and see my screen, please type Y in the comments. Yes. So let's recap. So today is the recap of whatever we have done, what we have covered in our syllabus, excluding the machine learning things we were discussing last two lectures. So basically, the signal processing perspective for speech production and perception. So So we started with if you, uh, our syllabus is basically what we have covered is course objective 1 and course objective 2. So uh, we covered the basic concepts of digital signal processing and production and classification of sounds based on uh, the articulatory or acoustic phonetics, the IPA chart. Then we covered short-time Fourier transform and capsule analysis and Mel filter banks, which comes under the speech analysis part. So we started with the psychoacoustic process of speech production and speech perception, where a better diagram is this, where that we have a message that is formulated in our brain that we want to convey, that becomes coded into sound units. So then neuromuscular commands are fired, and they basically command to move the muscles in our vocal rec system to produce those sounds. So that results, these are now continuous input now, whatever it was, let's say through information theory. If we calculate the information contained, message formulation will have a very few. It's like we gave an example of a telegram, just a hypothetical analogy that we did. A telegram in the olden days, if you want to say some urgent message, say come home quick, something like that. So only 3 words, 4 years, and we know that information theory, the lesser the choices, the lower is the information rate. The more the choices, the more is generally the information rate. So only 2 3 words, let's say, in a telegram. Then we have in sounds, let's say 40 50 individual sound units or phonemes are there in English. So information rate increases. Then we start moving our muscles, neuromuscular commands are given, they are again more in number. And then finally, when out of the vocal rack system, when we get the acoustic signal, each and every it could have any value, that acoustic waveform, pressure, vibrations that we finally record, that could have that is a very dynamic signal, a very non-stationary signal, and hence the information rate, you can say, is very high. So like that it happens. And then on the uh, while this is going on, a part of your voice you can also hear is a feedback loop is there, which allows us to train yourself, correct your error in pronunciation, in language and all. That is how you learn the language, because there is a feedback loop. And but going ahead, for the listener, you have again the opposite thing. There is a In the inner ear, there is a basilar membrane, which is the spectral analysis. We have now discussed about how it happens in MFCCs. So spectral analysis takes place. Then we have this uh, feature extraction. So basically, you can say uh, in basilar membrane does spectral analysis, and if I say MFCCs that the features extracted, we have DCT and all those that you do. That's an analogy. I am saying that something happens in the brain because so much information, it extracts the important features out of that information. That is the uh, purpose. And the feedback loop that we have, it helps you to train it. This is like a machine learning algorithm going on inside our brain. So anyhow, those are further mapped into the phonemes or the individual sound units, and then the final message is understood. So this is the psychoacoustic process that we discussed. We started with this in speech or speech processing course. We saw some interesting videos regarding all that. I hope please go through all that. It's all available, as you know. Uh, the lectures are all available online, uploaded online. So the next main thing we talked about glottal vibration. What is an EGG signal? So voice speech and unvoiced speech. In speech, generally voice speech or vowel-like sounds, they have a kind of periodic nature. Not exactly periodic like a sine wave. It is not exact like a sine wave, but you can see there is some periodicity there. That is in our uh, signal processing terms. We'll call that the fundamental period of speech. We also call it the pitch period, though that is a little bit let's say there is a little bit more technicality to it when we call pitch, but fundamental frequency or fundamental period is the term we associate with it. And a very accurate way of measuring is when you speak, you can there's a collar like thing, and you can tie that collar around your neck in the Adam's apple region, and you can see this kind of waveform. This is due to the vibration of the vocal cords or the vocal folds. So generally we find that uh, the speech waveform is mainly composed of, let's say, three different regions. Silence. Every speech signal that you utter, it will have silence between the words that you speak and before the uttering the speech and after uttering the speech. Otherwise speech will not be an intelligible form of communication. To be intelligible so that people understand, speech needs to have silence. And then the individual sounds that we have, we can mainly classify it into voiced and unvoiced. Voiced are those regions of speech signal or voiced yeah, where your glottal vibration, that is your vocal folds or vocal cords, vibrate at a particular frequency which depends or which varies from speaker to speaker. Unvoiced is those speech sounds where there is no vocal fold vibration. So this is also called classification based on phonation. It means your vocal cords vibrated or not, or vocal cords did not vibrate. Voiced, unvoiced. So we then discussed about in the classification of different sounds. We saw various videos, which are again I have shared the links regarding the IPA, International Phonetic Alphabet, and how we classify sounds in the International Phonetic Alphabet. What are the basis of classification? The IPA has a vowel chart and a consonant chart, and they are all divided. The chart is made based upon certain criteria. What are those criteria? We have some for vowels. You have roundedness and backness and all that. In consonant sounds, we have manner of articulation and place of articulation and other certain things. So then we discuss a little bit about formants or vocal tract resonances. What are vocal tract resonances? Vocal tract resonances are, you see, the vocal tract from the glottis to the mouth. It is like a tube of uneven cross-sectional area. But uh, if you go through any fluid dynamics or EM theory, electromagnetic theory, if you're familiar with the basics of those top disciplines, you'll know that any particular tube of particular area, length, height, width, all that, or cross-sectional area, it will have resonance. There will be certain frequency which will be amplified to a large extent, and that depends on the characteristics, the physical characteristics of the tube. So this tube that we have from the glottis to our lips, it will definitely have certain resonances. And in the production of voice sounds, generally during the production of voice sounds and vowels in particular, vowels, semi-vowels, glides, you can go through those classifications, uh, that these resonances are most prominent, and it is found that these particular resonances, particularly for the vowels, they have a particular pattern. You can classify, you can find out that different, there's five different vowels that we have. They have a certain range in which each of these resonances occur. Generally, every 1 kilohertz, you will find a resonant peak in the speech spectrum due to this during the production of these vowel sounds. In case of unvoiced sounds, there is also, of course, resonance is there, but those are not very well established in which regions they occur, which regions of the spectrum they occur. It is not very it cannot be, it has not been possible to heuristically identify regions in the speech spectrum where they will lie, kind of. So these are the characteristics of voice and unvoiced sounds in general. Now, an important thing here is, we talked about this. It's a very important concept regarding uh, if you see voice sounds, that is generally vowels, they will have in the speech waveform a lot of energy. For example, we saw this is a voice sound. You see, it has got quite a lot of energy. If you see unvoiced sounds, which is written as U, very less energy in the speech waveform. So, but which then carries the most of the information? The thing is, the voice sounds behaves as a carrier, like in communication technology. These vowels act like carriers, and the actual message information, that important information, is actually encoded in the unvoiced sounds, the consonants, so to say. So here, simple example kind of is given, where there is a in section one, you see all the vowels are removed, but you can still make out the information, the sentence, whatever it is, after removing the vowels. But in section 2 here, you removed all the consonants and kept the vowels. Now it is almost impossible to make out the sentence. Of course, this is a very crude example, because you see consonants are, so many consonants are there and only few vowels are there. So obviously, if you remove more information, then it will be more difficult. But this is a very crude example to let you understand or get a feel for where the message or information lies in the speech signal. So yeah, we talked about the international phonetic alphabet. uh, we talked about place of articulation, we talked about manner of articulation. We saw many videos regarding that from University of British Columbia. Let's go through all that. We discussed about IPA, importance of IPA. This chart, which gives a basic idea of the important classes of sounds that are there, this tree diagram. So this is generally people would expect you to know these uh, classifications. We talked about this vowel triangle. As I said, depending on the resonances, we are able to somehow we have found that these vowels that are there, they have a certain uh, range in which the vocal tract resonances occur, and hence we can classify them. We found this vowel triangle sort of. If we plot the first resonance on one axis and the second resonance on the other axis, you find that these vowels generally take a region around these particular points. Particular, they form clusters, kind of. So that was our preliminary uh, discussion on speech processing, its classification of sounds, and all that. After that, we we started our signal processing applications for speech. We discussed, if you recall, why speech is a random process. We discussed why speech is a random process, but since we will utter a speech signal only, let's say, only once, we don't keep repeating the same stuff. So we have to sometimes go for deterministic methods for analysis of signals. One of them is our sorry, yes, the autocorrelation function. This is the autocorrelation function where you have basically, if you look at the if you look at equation 7 below, autocorrelation of a discrete time signal, it is just basically inner product of the signal and its time shifted variant. And this deterministic function has a certain very important properties. This L, if you put instead of L minus L, the output will remain the same. So this autocorrelation function is a symmetric function. So you don't need to figure out negative lags. You figure out positive lags, you automatically know what the negative lags are. So using this autocorrelation function, we can devise a short time analysis of speed method to determine pitch. We discussed about that. So let's see if the slides are there. Yes. So before that, I think it's better I talk about short time speech analysis and the importance of windowing. So we talked about that the speech is a non-stationary signal. What does that mean? So that means that the characteristics of the speech signal varies with time. The Fourier spectrum of the speech signal varies with time. So this is why we need short time analysis of speech. Let's assume that we have a sinusoidal signal, infinite sinusoid. Obviously, if I have an infinite sinusoid, you know cos of omega naught n or sine of omega naught n, standard, you can derive that Fourier transform of that, and you have a unit impulse as the Fourier transform in the frequency domain at that particular frequency. If omega naught was your frequency, at omega naught there will be an impulse in the frequency spectrum. Suppose now you took a chunk of that. You don't have the infinite sinusoid. You took a chunk of that. Then will the Fourier spectrum, what will happen to the Fourier spectrum then? Well, then we'll observe something called windowing. But still, you will find that there is a peak at that omega naught in the frequency spectrum. That peak is now not an impulse. There is a kind of a dome shaped. So around that peak, there is also small value. The frequency spectrum has small some values around that peak, but you can still see that peak at uh, omega naught. Now, if you took another chunk at some other place, some other time, another chunk you took of that sinusoid, you will get the same spectrum. Nothing will change. But this was not going to happen in case of a speech signal. Speech signal, as you see, know, we are varying unvoiced, silence, and voice sounds. Very crude classification. And even if you go for detailed classification, there are so many ways we can classify based on acoustic phonetics. Each of the sounds, as you know, they are having different properties, different resonances, and so on and so forth. But so, if you take a chunk of a speech signal now and take another chunk of a speech signal at another place, you will never get the same Fourier spectrum. What does this mean? The previous case, when there was a perfect sinusoid, that was a stationary signal. This is not a stationary signal. So, hence, we cannot analyze this speech signal like a total infinite length, like that we cannot do. We have to analyze it frame by frame. And generally 20 millisecond to 50 millisecond is the frame size we take. And we shift the frames. Generally 50% overlap we do between frames. So if your frame starts from one frame, starting frame is 0 to 20 millisecond, the next frame you can say 10 millisecond to 30 millisecond. Like that we proceed. This is called 50% overlap. You could also have 75% overlaps between the frame, 25% overlap. All those things we discussed, why and where, which one is suitable. But this is the basic concept. Why we need to do short time analysis of speech? Because speech is a non-stationary signal. Now, why do we do windowing? The first thing is you took a frame of a speech signal. Now you could to give put a rectangular window, which means it does nothing. This is exactly as the you get exactly putting a rectangular window and doing framing is the same thing. Nothing. There's no extra thing to be done. But if you, let's say, put a dome-shaped window, we talked about Hamming, Henning, and all that. So if you put a dome-shaped window, what happens is the signal that is in the center of the frame, they are emphasized. So the Fourier spectrum, we don't want the Fourier spectrum to be influenced by whatever in the edges of the frame. That's the basic goal. So we want the center of the frame to be representative of the whole frame, kind of to say. This is in time domain. That is the basic goal in time domain. What is the other goal in the frequency domain? What is the other goal that we have? That goal or that advantage comes from when we look at the frequency domain. So what happens is, let me see. Yes. So we discussed about windowing in quite a detail. Actually, it's a very important subject. So if you have a window, see it is a sinusoid on top, on the left hand corner, that will give a impulse, that arrow at 13 hertz. When you window it, you took a chunk of it. Now around 13 hertz, that blue color, you can say around 13 hertz, you will get a peak. You will get a peak at 13 hertz. And but there will be also these side lobes. These side lobes are because of when you go to short time Fourier transform, it results in convolution with the frequency, that Fourier transform of the window. When you do windowing, the Fourier transform of the original signal is convolved with the Fourier transform of the window. This results in all these side lobe levels, which we also call spectral leakage, and a wide main lobe. And instead of a what is called impulse at that frequency, you start getting all this sync or these lobes. The width of the main lobe is determined by the length of the window. The larger the window is, the smaller will be the main lobe, and all these effects that are there, the side lobes that you see, that those will also decrease substantially. The smaller that is, the wider this main lobe and other side lobes are. So there is a trade-off we have to do. On one hand, we cannot have a large window because the speech is a non-stationary signal. And on the other hand, if we have a very small window, it means that we'll have a very strong effect of windowing. So both are advantage. Both. So we need to have a good trade-off. So now coming to, these are the things we discussed regarding short-time Fourier transform. This is short-time Fourier transform is the Fourier transform of Sm Wn minus m, which is the windowed part of the signal. We have talked about all that. Revise, please revise. So this is a short-time Fourier transform. Remember, generally log magnitude is used. Yes. So previously was, you see, 500 sample length or 50 milliseconds was taken as a window size. This results in this kind of spectrum. When you reduce the window size, because of the strong windowing effect, you get a very average kind of. Now this is also advantageous. We will see in spectrogram what happens because of that. Now we were discussing about different types of windows, and you see rectangular window, the side lobe levels are generally high. The advantage of dome shaped window is the side lobe levels are substantially lower than the rectangular window. So Hamming and Hanning both are very useful windows, or very popular windows that are used in speech processing particularly. There's the equation, standard equation of both the windows. You can uh, it's called, go through that, revise this part. So we then went for spectrogram. Spectrogram, as we saw, there is a wideband spectrogram as and a narrowband spectrogram. How do we get that? Wideband spectrogram means the window, main lobe of the window is large. Then we get a wideband spectrogram, and then we see vertical stripes, striations, which help us to see how the formants are changing over time. In narrowband spectrogram, the window main lobe is low. In the Fourier spectrum, the window main lobe is small, and we see horizontal striations which help us to determine the fundamental period of the speech signal at different fundamental period of the speech signal, and that is also the fundamental period of the or fundamental frequency of the speaker. So we talked about all these things, how spectrogram behaves with respect to the type, and with respect to the different sizes of the lengths of the window. Now, we talked about two other things in short term analysis: energy and zero crossing rate. In energy, if you see speech signal, any particular speech signal, so this silence will have almost nil energy. This unvoiced will have more than that, and obviously the voice regions, which are periodic in structure, will have more energy. The zero crossing rate, again, silence and unvoiced, it's difficult to separate clearly by thresholding, but definitely silence or unvoiced versus voiced, you can see the zero crossing rate is far greater for unvoiced or silenced regions compared to the voice regions. What is zero crossing rate? We went through that. So we gave an example we'll take an example of a sine wave or something. The number of zero crossings gives an idea about the frequency of the signal. So we used that concept and applied it here in speech processing. In case of unvoiced, which is noisy nature, a lot of you will get a high frequency. In case of voiced, you will get much lesser, relatively much lesser frequency. So we talked about this short time analysis of speech, and then moved towards our source filter theory, which encompasses basically this. uh, we have, if we are generating a voice speech signal, a train of impulses which is representative of the periodic vibration of the vocal folds. Now, when if we remember our EGG signal, it is like a window kind of, and it's like a puff of air. So basically, when the vocal folds vibrate, a puff of air is released into the vocal tract system. So that is modeled by a window, a glottal pulse model, which is asymmetric window. And then we have a gain term. It's okay. We multiply it. It's a constant factor. It might be related a little bit to how loud a particular sound is, and so on and so forth. For unvoiced, there is no, the glottal folds do not vibrate. There is nothing, no uh, the glottal pulse model then do not exist, so to say, or you can put it simply as one. That means a random noise is used to represent the excitation source, and a gain term is multiplied with it. This then passes through our vocal tract system, which is a cascade of resonators, and a lip radiation model, which is like a high pass filter. Why a high pass filter? I give a simple example. It's like if you have a water tank and a very small tube where the water is flowing, it will come out with large velocity. That's a very crude analogy I am giving. So lips are also like that. When the air finally comes out, you don't have your mouth wide open all the time, compared to the infrastructure that is behind the lips. It's a small orifice, you can say. So on the other hand, the glottal pulse model is a window shaped, dome shaped. It is represented by the low pass filter, and we discussed all that. What are the uh, what are the transfer function equations, how do we model them, and so on and so forth. We discussed about the resonant frequencies of the vocal tract, that every uh, kilohertz, generally for every kilohertz there is a resonant frequency. Similarly, if you recall, the pitch or fundamental frequency is generally lower for males, around 100 hertz, than adult females, which are around 200 hertz. Why? Because adult female, the vocal tract is shorter. The physiology of female human females is generally human females are generally smaller than males, and all their or biological characteristics are of the vocal tract, it is shorter compared to males, and shorter tubes generally produce higher frequencies. So that is why generally in females you have both vocal tract resonances and or pitch, that vibration of the vocal cords at a faster rate, and pitch frequency is higher in females. Children, it is even higher. So if you have 100 hertz is the adult male fundamental frequency, 200 hertz is an adult female fundamental frequency, and much higher, so around 400, 300, 400, 500, okay, sometimes hertz for children. So we discussed how we model all this, and then we went to the linear prediction analysis of speech. So we discussed that we have the source filter theory that we have. It enables us to use linear prediction analysis, which is a very well-known algorithm in adaptive signal processing. So uh, we saw that in linear prediction analysis, we can represent a current speech sample, value of a current speech sample, in terms of its previous values of its previous samples. They are correlated in some way, and uh, it is complemented by the source filter theory, and we saw how mathematically it is complemented. So what are the number of samples that will take? That depends on the number of resonators we think are there in the vocal tract system. Plus you can have some real poles and so on and so forth. So there is a heuristic method of figuring out. If you are thinking, let's say 8 kilohertz signal means 4 kilohertz maximum frequency, each of them, each 1 kilohertz there is one resonator. So eight poles within 4 kilohertz, plus we add 3 or 4 more poles for modeling the spectral slope. The speech signal has a slope, particularly for voice speech, of -6 dB per octave. So to and real poles generally cause those spectral slopes. So because of that, we have a heuristics of determining the value of peaks. But regardless, the main point is we can represent a speech signal in terms of its previous samples, and then we went ahead with determining those values, those weights, based on which the current speech sample can be estimated. The weights of the previous samples based on which the current speech sample can be estimated. and that gives us our linear prediction analysis. We use mean square error, the reduction of the mean square error, or we find optimal mean square error, and we determined the values of alpha k or the LP coefficients. And many advantages of LP analysis we discussed. We discussed a little bit about the Levinson-Dublin algorithm also. We discussed about the Parkour coefficients also. So again, we discussed how LP analysis is related. This order of the LP analysis, how it affects the final analysis, how it is better or more accurate for voice speech than unvoiced speech. What happens uh, if we so there is an example for here where we find that the LP analysis is able to give us the spectrum, the what is called the envelope of the spectrum of the speech signal, whereas the LP residual that we get from LP analysis, they show peaks at around the pitch periods of the speech signal of the voice region of the speech signal. So these are the things we discussed. We discussed also what happens if we have an inaccurate order for the LP analysis, if we have less, if your order is too low, or if your order is too high. So this is the generally the as you see, this is a correct or accurate uh, way to model the or to figure out the order of the LP analysis. So basically, every kilohertz will assume two resonant poles. So based on that, you can get a heuristic of what should be the number. So then we discussed about Capstone analysis of speech or homomorphic analysis of speech, which is again a way to segregate the vocal tract system characteristics from the excitation source, because deconvolution is not easy. Summation of two signals, okay, it's relatively easy, but convolution, which includes multiplication, summation, and even time shifting, so when two signals are convolved, it's really difficult to separate them out. So we using capstone analysis and using liftering, we find a way to model or to estimate the envelope of the vocal tract system, which gives us another tool for estimating the vocal tract resonances, just like in LP analysis. So then we went ahead in our last week, mainly dedicated to the MEL filter bank and MFCCs. MEL filter bank comes from how the basilar membrane, the perception of speech occurs in the basilar membrane. It's like a frequency analyzer. We discussed in depth about how perception of pitch is actually different from the perception of the fundamental frequency, even though we loosely equate it as the same. We discussed about the critical band theory. We discussed about the subjective pitch or subjective frequency scale that we have in the human ear, which is represented by this MEL filter bank. We discussed about masking, particularly frequency domain masking. We saw videos regarding that. We discussed about why free pre-emphasis is required to reduce the what is called, yeah, reduce or overcome the spectral slope of voice regions of speech signal. And then we do analysis, even LP analysis we do after pre-emphasis. So then we discuss the steps of finding out the mel frequency capsule coefficients, which has pre-emphasis, windowing, applying the Fourier transform, putting the mel filter bank on top of the spectrum, and then using triangular filters, and finally using discrete cosine transform. And once you get the MFCC coefficients, we can then derive delta coefficients and delta delta coefficients, which again give us how, if the MFCC represents the characteristics of the vocal tract or the speech signal at certain point of time for a particular frame, delta will represent how those MFCCs, the vocal tract or the speech production system, it all is changing, and delta delta will represent how, at what rate they are changing. So that's all. That's a review of uh, the entire speech processing course till now. So uh, we will conclude the lecture here. Please give your attendances and please exit the lecture.